Okay, now we're going to take a look at another application. It's a pretty key relationship of how integrals can allow us to find what we call areas underneath a curve. So when we find out an area under a curve, it's defined to be a very specific area. It's the area between the curve itself and the x-axis. So if you look at my picture here, I have an original graph, which I've called y is equal to f of x. And I've denoted this gray area here as a of x. So if we want to find the area of this grayed out part from a to b, so a is my low limit, b is my high limit, so I'm only going between the two values, I need to derive something here. So I know that this is the area. I'm going to call it a of x, okay? And a of x is really a of b. So it's the area from a to b. This is what area a of x is actually supposed to represent here. So what a of x actually is, it's the antiderivative of f of x. So this area is the antiderivative of the original graph. So in that case here, I can actually use a different notation. So a of x, which is the area, is equal to the antiderivative of f of x. So to show the antiderivative of small f of x, I use a big F. So I know it's a little confusing, but don't worry, we'll clean this up a little bit here later on. So therefore, the area is equal to the antiderivative of the original graph plus the constant c. So we have an initial condition here to allow us to find c. The initial condition, which is my low limit here, is that a of x is, for a of x, is that a of a, which is the point that I chose here as my low limit, is 0. So what it just means that this is an x-intercept right here. Okay, it's starting at my x-intercept, so this is my low limit. At an x-intercept, my y value is equal to 0, which makes this statement true. So using that initial condition, I'm now going to derive a much cleaner formula. So my area function is equal to the antiderivative plus my c value. I want to find c or define it as something. So I'm going all the way, I'm starting from little a, okay, is equal to f of a. So I'm just replacing all my x values with little a, plus c. And I know that my initial condition, which is my y value for a, is equal to 0. So I'm just going to make everything equal to 0. Okay. So this is f of a right here, plus c. So therefore, c is equal to negative f of a. So therefore, this is what my graph is going to look like now. A of x, which is my area function, is equal to the antiderivative minus whatever my antiderivative is evaluated at my low limit, which I've called a. And finally, well, x is really b. I'm going from a to b here, so therefore the area of b is equal to f of x, which is f of b really, minus f of a. So this right here is what we consider the definite integral. Okay, so let me just sum this all up in my next slide. The fundamental theorem of calculus, it states that a is equal to f of b, so this is the antiderivative evaluated at b, minus the antiderivative evaluated at a, is referred to as what we call the definite integral. So when you find a definite integral, you're actually evaluating your integral, so you're actually finding a value. When you find a value, it results in a number. So we have done integrals, but now we're actually going to evaluate integrals. It's actually called the definite integral. So far, we've always just dealt with indefinite integrals. So if a function is continuous on an interval a to b, where a and b are defined, then f of x is the antiderivative of little f of x. Then I can actually show the fundamental theorem of calculus in this way. I'm going from my low limit, a to b, to my high limit. Okay, so this is my low limit, or my low value to my high value of my original graph with respect to dx. So this right here is what we consider the fundamental theorem of calculus. So the antiderivative of f of x, or sorry, the antiderivative which we called capital F of x of any function little f of x gives the area under the curve from A to B. A and B are called, I've just kind of referred to this already, but we can review it. So A is called the lower limit, while B is called the upper limit, okay? So we're going from lower to upper limit. We're going to actually evaluate integrals now. So let me show you what this could look like with these two questions here. Evaluate the given integrals. When evaluating, you don't need to actually find the value of C. So we don't have to worry about C here, because what happens with the C values, they end up canceling out when we actually do the calculation. So I'm actually going to show you the C value for this one here and why it doesn't apply. And then from now on, we won't show C. Okay? So the notation is going to look like this. I'm going to take the antiderivative or the integral as we've done before. So for 2x, I get 2x to the power 2 divided by 2. And then we're going to add 5x. And then I'm going to add C. So once again, I don't need to show this. I'm just going to show it for this one example to see why we don't need it anymore. And then we're going to go from our lower limit to our upper limit of 3. Okay, so this is my notation. I just put a vertical line to show that my lower limit is 1, my upper limit is 3. Okay, so before I evaluate here, I can actually simplify this a bit more, because 2 over 2 reduces down to 1. So I get x squared plus 5x plus c. And we're going from 1 to 3 again. So I'm actually going to put in my numbers. So the first number I put in is my upper limit. So I go 3 squared plus 5 times 3 plus c. And then I'm going to subtract my evaluation when I put in my lower limit. So I'm going to put in 1 squared plus 5 times 1 plus c. Okay, so out of this, I should get a single number. So I'm going to simplify. I get 9 plus 15 plus c minus 1 squared gives you 1. And then this minus distributes into here, by the way. So I get a minus 5, which is 5 times 1, and then a minus c. So we should see why, once again, we don't have to write the c value all the time anymore, because the c values, because of how the fundamental theorem works, actually ends up canceling out. So my answer is going to be 9 plus 15 minus 1 minus 5. Oops. And my first evaluation here is going to end up being positive 8. So that right there is my value for my definite integral of 2x plus 5 from 1 to 3. So I'm going to try one more right here. From 1 to 4, evaluate the integral square root of x minus 1 over x with respect to x. Okay, so first thing I'm going to do is simplify. I'm not going to integrate yet. I'm going to simplify this function right here. So this is the same thing as going root x over x plus 1 over x. Of course, we're integrating with respect to x here. And I'm going to go ahead and simplify this. So I'm not going to evaluate just yet. I'm almost there. Got one more step. This actually reduces down very nicely to 1 over the square root of x. Okay, so instead of me writing that, I'm actually going to write x to the power of negative 1/2. So remember, this is really a power of 1/2. I get rid of the square root. 1/2 minus 1 gives you negative 1/2. Then I'm going to add 1 over x. So I'm going to keep that the same, because this has its own antiderivative, its own special function that defines it. Okay, and now I'm going to go ahead and take the antiderivative. So the antiderivative of x to the power of negative 1/2. How we write that is, well, if I add 1 to negative 1/2, I get 1/2. And then if I divide by 1/2, I'm really multiplying by 2 over 1. So I get 2x to the power 1/2 for the antiderivative of that function. And then I'm going to add the antiderivative of 1 over x, which gives me the ln of x. Then I'm going to add, but oh wait, I'm doing an indefinite integral, so I don't have to add the c because it cancels out as we saw with the previous question. So really, that's what I have right there. So I'm evaluating from 1 to 4. Okay, so now we just put in our values. So we always start by putting in our upper limit, which is 4. So 2 times 4 to the power 1/2 plus the ln of 4. Then we're going to subtract the integral when you evaluate at 1. So we have 2 times 1 to the power 1/2. And then we're going to minus, we're going to minus positive ln of x, which just ends up being a minus of ln of 1. And we can actually simplify this. So what we get here is 2 times 4 to the power 1/2 is really 2 times 2, which is 4. Then I'm going to add the ln of 4. I'm just going to keep it as an exact value. And then I'm going to subtract, well, 1 to the power 1/2 just gives you 1. So I get 2 times 1, which gives you 2. And then minus the ln of 1, which is just going to be ln 1. I'm just going to keep everything exact, just so we have a nice answer in the end. Okay, so my final answer, keeping everything exact, is going to be 2 plus the ln of 4 minus the ln of 1. Okay, so that's pretty much it. Actually, ln of 1 does evaluate nicely. I just realized that ln of 1 is going to give you 0. Ln of 1 is 0, so I get 2 plus ln of 4 as a final answer for that guy.